Okay, so this is where we ended last time, and so just let me finish the isomorphism for the case of fermionic algebras. How do we do all these transformations, and how do we find the unitaries efficiently using linear algebra? And we could move on to, essentially, could be done with the measurement problem for now, and move on to the essentially fault tolerant algorithms. All right, so but how do we find these unitaries that essentially for any electronic Hamiltonian diagonalize the problem, and it's based on a very useful isomorphism. There are these operators that one electron excitations one can introduce, AP, AQ, right? And our orbital generators are just then the differences of excitation and the de-excitation. And this is Hermite conjugate version Q, right? Also, we'll use the occupation number short notation for the diagonal terms, right? So this is our generators. The unitaries that we want to find is either we can write them as a products of these terms, the PQ, generator PQ, or we can write them also as the exponential function of a sum in P more than Q, and theta PQ, GPQ. Okay, so either in the product form or in the form where this whole sum is put in exponential function. So these are equivalent parameterization of, as turns out to be a Lie group, element. And this is corresponding Lie algebra. These are generators of Lie algebra. And because of that, essentially, we can write any Lie group element as a product of exponential functions or exponential of the sum. So here, clearly, the order doesn't matter, but here, order will matter for what parameters we should put if we have particular unitary to implement, okay? But essentially, what allows us to do all these manipulations, the fact that if we do the commutator of GPQ with some GRS, it will be proportional to some coefficient that essentially will be equal, let's say, sum over I don't want to write the indices here, but with some coefficients, we have essentially G and yeah, I guess N is some index, right? And this formula is just kind of one way to well, you could obtain the coefficients, you can obtain what G's are. It's just simply what is well, kind of well known is that these EPQs they form a Lie algebra with this kind of commutator relation that we I think discussed at some point. PS delta QR minus S PS minus R R with Q delta PS Okay, so we have this for sure. And then from this, you could always derive what these elements are, because G's are linear combination of EPQs, right? So because there is a relation here. Okay, so but now this is all kind of known conditions. And how do we find the n goes? How do we do these manipulations? The difficulty is that these operators, they still live in a Fock space, right? So it's a giant 2 to the n, where n is a number of spin orbits space. And representing them as matrices there is going to be not very efficient for computations. Turns out, instead, one can represent these operators in matrices n by n, right? So instead of matrices 2n by 2n, right? So this is a Fock space, or corresponding Hilbert space of the qubits, if you want. But this one is kind of smaller space, and it allows still to represent the G elements as matrices. So how is this done? It turns out that you could organize the isomorphism for every operator EPQ. You put as a corresponding element a matrix, which in linear algebra is also called EPQ. And these matrices, these are very simple matrices in n by n matrices in n-dimensional linear space, where you take the p row. Oh, sorry, this is a column, and you put and you also take the row, right? And you put identity in that element, and everywhere else it's just zeros. Okay, so these are the matrices, and it turns out you could check taking some sort of linear algebra package like MATLAB, very convenient. You could check that for this for these matrices, you will have the same computational relations as for the operators, right? So therefore, we can define binary operation between the matrices. Let's say it's a operation like let's say dot. Okay, dot is a bad. All right, so let me just say that the commutator between the matrices could be put into the correspondence between for the commutator of the operators. What this means is whatever you obtain here as a result, we obtain some sort of operators with linear combination of them, right? With some coefficients, it's written there, right? So whatever we obtain here, we can transfer that into the matrices, right? So this is our isomorphism. So we could construct corresponding matrices with the same coefficients, and that will be exactly the same result as this is equal to result here, where we just operate with the matrices. Okay, so that's the value. So you don't need to do any more operations in the operator space, right? So you don't need to think about daggers or these commutators. You could do all the operations with matrices, which is definitely convenient because you could do it on a computer, right? So if you have a complicated operator that contains these guys, then you could see what's the commutator of let's say one electron operator and another one electron operator. You could use matrices for that. Okay, and that's the value of this isomorphism. Now there are constraints though of that isomorphism because it's based on a particular operation. It's based on like a binary operation that is a commutator. So another operation that one may want to do with matrices is just a matrix multiplication, right? So matrix times matrix gives you third matrix, and you could try to multiply, and the result, if these matrices came from some linear combination of operators using our isomorphism. So let's say CPQ, EPQ operators, right? So you could construct a matrix corresponding to this. This one could be also done as another set of coefficients, maybe EQ. And then you multiply them as matrices, like in a normal linear algebra sense. You get the third matrix, and you may want to write this as a kind of, let's say, another set of coefficients EPQ, like this. But then you realize this will be incorrect in the sense that if you try to kind of multiply this operator with this operator in operator space, this is operator space, this is matrix space, right? So if you multiply them with the normal operator multiplication, what you're gonna get is instead just a linear combination of EQ, RS, so two electron operators, right? So here will be CPQ, then TRS coefficients, right? So you will get the two electron operators. You won't get the one electron operators, okay? So therefore, one can conclude that matrix multiplication is not something that could be mapped back to the operator space. So you cannot multiply matrices. So what you can do, though, is you can take the commutators. Okay, so the commutators is a legitimate operation. You can take the commutators between matrices and come back to the operator space. You cannot just simply multiply matrices and come back to the operator space, because that the result will be incorrect. All right, but so then if we are limited to just commutators, how is this useful at all? Okay, so it turns out it's useful because if you want to, let's say, use this for presenting unitary elements, if your unitary elements are presented like exponential function of some, let's say, as an x, I will denote, say, some element of this the algebra, right? So it's a linear combination of operators. And if I want to use this for presumably diagonalizing the kind of the one electron operator in some form, right? So then usually we diagonalize using the unitary transformation, right? So this will be unitary operator of orbital rotations of some sort. This one as well, just conjugated. Then this expression could be written as not just a multiplication of operators. This expression is called, sometimes it's this expression I'm going to write, it's called Campbell-Hausdorff expansion, but the proper name really is a Campbell lemma. So one guy, Campbell lemma, That's the proper reference to this expression. So what Campbell lemma is saying, and it's relatively easy to show by introducing the parameter and just differentiation. So it's the commutator of generator with H, then it's 1/2, and then the nested commutator like this, and so on with more nested commutators. Like next one is our factorials essentially. The x1, 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 h1e, and so on. As you could see, we only use commutators. Okay, so therefore, it is legitimate to do this operation using essentially now the matrices corresponding to the same element of the algebra, and the matrix corresponding to this one electron term. It's a H matrix, exactly the matrix of the coefficients here, right? Because then what the result of this conjugation will be is that we will have H matrix plus the whole yes, M1 H and so on expansion, right? So we will never just multiply M by H, right? So we always will take the commutators, and the commutators they will we have a closure with respect to that. So commutators will not introduce elements outside of the Lie algebra. So whatever this will be is essentially a Lie algebra element, and all we want from the element that we've chosen, so that the Lie algebra element will correspond to just occupation numbers, right? So that in a matrix formalism, that will be a matrix with only diagonal elements, epsilon 1, epsilon f, right? So because n and p corresponds to EPP, right? So matrix element with 1 on the p column and p row, so it's a diagonal, right? Therefore, we can find a matrix that if you exponentiate that, it will give you the transformation that diagonalizes the H corresponding to the 1 electron integrals in the 1 electron operator. Okay, and so using that, you could diagonalize. Now, few other comments here is, of course, this matrix needs to be anti-Hermitian. Otherwise, it's well, e to the m is not going to be unitary otherwise, right? So this condition needs to be satisfied, but it is satisfied if we produce m from our sum over some real with the real coefficients. Imagine p and q are real, and then the matrices that correspond to the GPQs, and these matrices are essentially 1 and -1 on the corresponding PQ and QP positions, right? So these are just coming from the matrices PQ minus P. Okay. So this is how we select these matrices, and they are with the theta PQ being real. We always satisfy this condition. And also, we could see that there is another isomorphism here one can organize. It's isomorphism of any sort of group elements. So this is the unitary group element, orbital rotations, operators, multiplied another generator. And so if we multiply one unitary by another unitary operator, we still have unitary, and that unitary generally can be written like this. This is U3. Now, why we can correspond this in operator space to something that is way easier, of course, to do with the matrices. Because there is a condition how the M3 is written in terms of M2 and M1. Okay, so the same actually true for the operators, of course, right? So if you kind of deal with any non-commuting object like this, so there is a now proper Campbell Baker-Campbell-Hausdorff, right? So Baker-Campbell-Hausdorff expression, right? And that expression tells us that if you take the EA, EB being non-commutative, then you could write it as exponential function of C, and the C will be A plus B plus commutator of AB plus some essentially coefficients that are effectively, let's say, alpha 1 plus then you have essentially nested commutators of A probably B, A expressions. But the point here is that these expressions require only nested commutators of essentially the things that we have in the exponents, right? So therefore, if these elements are from Lie algebra, then this element is also from Lie algebra, because we cannot get outside of Lie algebra by making the commutators, right? Therefore, if we could predict what result of we're going to get with matrices that we can easily manipulate with, then the same result, then we can map M3 to the X3 in operator space, right? Therefore, this also works with the exponential functions. Like essentially, we could continue this isomorphism not only for the group of, not only for the algebra of operators, but also for the group corresponding to that Lie algebra. Okay, and so that way we can always try to find essentially unitary that diagonalizes the matrix of one electron Hamiltonian, and then that particular unitary you could take a logarithm of that in order to get the corresponding Lie algebra element that will be the element that you can then correspond to the operator expression in terms of the PQ and GPQs, the generators. So that's the process. Okay. One needs to just be careful that not every operation in the matrix algebra we can do and legitimately map to the operators, right? Because the isomorphism only works for certain operations. It's multiplication of the unitaries or commutators between the generators of algebra. So you need to make sure you're doing you are aware of what operations you are mapping. Okay. All right. so that sort of finishes this topic of measurement. Now essentially the bottom line here, one can say, is that isomorphism between the operators and small linear spaces helps us in both cases, actually in full commutativity case, to find the unitaries which are Clifford unitaries. And in the case of fermionic rotations, again, we're using isomorphism between operator space and space of small matrices. And linear algebra is very efficiently can be done in the small matrix spaces. Okay. All right. With that, to summarize, this is essentially some summary on the whole measurement part, and effectively can be optimized. If you want to minimize the number of measurements, you not only need to think about the groups that one can do, but also on the variances that one gets, and there are interesting optimization techniques for fermionic or qubit transformations. So one can use those, but I guess main challenge in the near term, at least, is that some of this transformation that allows you to measure big part of the Hamiltonian, they are requiring extra circuits, and that is still because we don't correct the errors that occur. We are sort of experiencing issues with that in the practical applications. Okay, but there are some success stories that we could probably reduce the number of measurements from the billions to millions in some cases. That still doesn't account for the these estimates. They don't account for the actual practical extra measurements one needs to battle essentially the noise that will occur with the unitaries that allow such reductions. Okay. All right. Now the next thing, big topic, fault-tolerant algorithms, and the simple motivation. You already probably motivated that. Well, if we don't correct errors, they prevent us to do stuff like even the measurement case, or prevent even to get the good results. But just to capitalize on that point, it's actually pretty bad in the sense that if you think about that quantum computer supposed to give you an algorithm that can compete with the classical, right? Now that's the idea. And many people, when they kind of learn about VQE, they start kind of getting into the business of creating various ansatzes for the wave function, especially in chemistry, quantum chemistry community, somewhat ignoring the problem of noise and problem of measurement. That's all fine. And so essentially the game was to show that you could get smaller and smaller error when you introduce these more complex operations that you can do on a quantum computer. So unitary transformations, right? So that was the game. But if you account for the noise, right? So then you would know that at some point, if you just put the advantages from the operations with the disadvantages that you're going to get from the noise, the picture will be not as kind of idealistic as the kind of the simulations will show you without noise. And so initially you will increase the accuracy, the error overall will go down, but then no matter how smart you are, it's not about your ansatz, it's more like, okay, the number of operations you will need to do is going to grow. And with that, the noise will catch up, right? And well, the curve will be like this. So there is a sweet spot, of course, and we could imagine with improving hardware, we could probably move that sweet spot somewhere further and further, meaning that we could address larger and larger systems. But if you think from the point of view of what electronic structure theory wants, it wants scalable algorithm, meaning that if you could do system A, well, then the question could be, what is the cost for doing 2A? Okay. So if you here with A, then 2A will be somewhere there, unless your algorithm scales either constantly with the size of the system or logarithmically, right? There is this error problem that creates exponential growth of the error, well, essentially error. And therefore, there is no hope to create a method that is scalable and can compete with the classical methods, because classical methods, they all polynomial in the generally in the scaling, and there is no issue with the error. So we need to do the error correction. Also, it allows you to make bigger circuits, and turns out that the bigger circuits, you could think somewhat differently with them and create the algorithms that are, well, not just substituting what we do in electronic structure by unitary transformations. There are other approaches one can explore, right? And this is what essentially we'll be talking about. The first algorithm, the textbook algorithm that everyone learns, probably is quantum phase estimation. And quantum phase estimation looks like this, where this unitary is just an exponential function of Hamiltonian, let's say, the system. Right, so that's our unitary. And it looks quite complicated if you look at it. Like there are lots of qubits. Like this is the system. There is an extra qubits, and then there's some transformations and quantum Fourier transformation, which is inverse, and then there's a measurement involved. So essentially, my claim here is very simple. It's not obvious how this thing works, and it's more like you see in some trees, but you don't see really a forest. How did anyone come up with this thing, right? So what's the idea behind it? So that's what I wanna explain, because many books and review papers, they just say, okay, well, this is obvious. This will give you the answer, and they can go into the details of each step, and then my favorite example would be probably analogous to what you achieve by going to those steps. Like imagine someone, instead of saying that, okay, what I'm doing here, I just want to rotate the vector in multidimensional space by unitary transformation, right? So just one sentence. Instead, they will say, all right, here's what we do. We have a column of numbers. We take first number here, and we multiply. There is a table. We multiply it by this number, and the second number multiplied by here. So they will explain this procedure step by step very clearly, but there is kind of no insight, right? So it will be very tedious. And it's like, okay, but aren't you talking about just a rotation? If this matrix is unitary, it's just a rotation of the vector. That's it, right? So you don't need to tell me how you do step by step this procedure. Just tell me what it means. Like, there is a clear geometric meaning. And it turns out there is a clear meaning in this quantum phase estimation algorithm. And well, somewhat simplified pictures could be given like this. So imagine if we are interested in getting eigen values for the Hamiltonian, right? So that's what we are doing in the quantum chemistry. And so we could start with some wave function that is linear combination of states, clearly, because the Hamiltonian forms the complete set, right? So you take any function, it's a linear combination of eigenstates. And then what you can do, you can form this object that is called an autocorrelation function. You apply this exponential function of h to psi, kind of bracketed with a psi, right? So essentially you propagate the wave function for some time, and you take the overlap with the initial wave function, and then do Fourier transformation. Turns out, if we do few lines of algebra, which is just putting this expression here and applying H to it. So H, when it meets every eigenstate, it will produce the phase exponential 5 En into the t. And then you sort of get the Fourier transformation of these exponential factors. So you get the delta peaks, right? So the delta peaks will appear at the positions of the eigenvalues, right? So this is the spectrum on the right that you're going to get the picture. So that's easy. So this is essentially the idea behind of quantum phase estimation in a very simplified form. Now it involves, this procedure involves unitaries, like this is a unitary because I times H is an anti-Hermitian, and then there is a Fourier transformation, which is also unitary. But this simple idea doesn't explain, okay, like how do we implement all this as a circuit? How do we do, how the measurement will end up getting us these peaks, right? So those are still like questions that one can ask, like how do we really connect this with the circuit that they're showing, all right? And the circuit they're showing is a little bit more complicated. So actually it turns out for the circuit that we have here, time needs to go not as a parameter, but as a separate Hilbert space, okay? So it turns out that you cannot treat the time as a parameter, but instead it should be its own sort of, it's in its own space. Therefore, if you want to really explain textbook quantum phase estimation, so something that is more useful is to look at how the measurement in general done, because what quantum phase estimation is doing really, it just measures energy of a system that is prepared, right? So imagine someone prepared the state, and someone and then decide, okay, I want to measure what's the Hamiltonian, I guess, eigenvalues, right? Because in measurement we always get an eigenvalues of the operators, and this quantum phase estimation is nothing but just a way to do this measurement, okay, practically. All right, so in order to understand how it works, we need to look at what's kind of known about quantum measurements. So there is this von Neumann kind of way of thinking about the measurement. And here a notation is, let's say we have a phi, just and psi n's are the eigenstates, all right? And what we're gonna do essentially is that we prepare this special operator, which contains a tensor product of the Hamiltonian with the shift operator. So that shift operator is actually the way to record the measurement in somewhere. And for recording the measurement, we need result of the measurement. We need an extra space. Okay, so these are the extra ancilla qubits. And what is happening then is we apply this right now magical operator, right? So this complicated but unitary operator. So potentially we have a chance to implement it in a quantum computer. We can apply that tensor product sort of operator. And then what's going to happen is, well, this phi is linear combination of eigenstate as before. So when this magical operator of ours meets every psi n, which is an eigenstate, right? So when that happens, its H part will turn into the eigenvalue, right? And then that eigenvalue will be a coefficient in front of the shift. So if the eigenvalue is larger, then the shift will be acting more, right? And eventually, what's going to happen is that according to this eigenvalue, the shift will act differently on the different products of the ancillas on top of the what state we have, right? So because we started with the phi and then 0, And then this state is really Cn psi n 0. Essentially, we have each psi n associated for each psi n in this sum. We have the register which can record the results, right? And this register will be changed differently based on what eigenvalue psi n will have, right? Because that's what h will be doing. And then this state will be shifted accordingly by the eigenvalue. And those states that will appear, they potentially can be made orthogonal. And so then what's going to happen is the states that we obtain in the ancillary register, they will represent binary. In a binary representation, they will represent the eigenvalues corresponding to psi n. Okay, and with probabilities of Cn squared. So if you now measure this superposition with probability Cn squared, you will essentially be able to measure the zeros and ones on ancilla. Okay, so that is overall what's happening in the quantum phase estimation in that circuit. It's von Neumann measurement. Now there are issues still, because this magic that I wrote, it's in abstract sense. Like I just wrote what I wanted to do, but then the question is, how do I really make such operator, right? And then there are a few other which are we address as well. So one problem is, of course, the phi needs to have a good overlap with the state that was of interest. So this is something that was asked somewhere in the beginning of this lecture series. So there are ways to, of course, prepare a good initial state, but it's an interesting problem on its own. How do we really estimate how good is the state that we're starting with? Does it have a good overlap? This is not something that probably I'm going to discuss today. And there is a third aspect. Okay, so the Hamiltonian actually is not trivial. It's not trivial to put an operator like h into the exponential function. And so some approximations or some ways to encode h there would be necessary. But one of the, I guess, the first things is how do we really, let me go back. So how do we really create this shift operator? Because this is like essentially the main kind of element there that if we will be able to put into the exponential function h, well, we know h what it is, but how do we create s operator that shifts the ancilla or auxiliary, these zeros, into the essentially encoding the energies for each state? So this is the part that needs to be addressed, of course. So this brings us to how do we really think about the shift operator. And if we go back from quantum computing to just simply quantum measurements, what do people do in the lab? How do they really do the experiments? So they create the system, and then they have a device, right, with the pointer. And so then when they connect the system with the device and say push the go button, right? So then the pointer eventually goes and shows what's the eigenvalue of the operator is, right? So that's how we are taught in quantum mechanics for undergraduates, right? So there is always a device for every operator that will be able to do it, right? So in reality, of course, it's complicated to do such devices for complicated operators. Mostly it's very simple operators that we can build devices, but still, even for simple operators, how does that device will operate? That's the question. And here's the answer. Okay, so the answer is the following, that you could think of that there is the device Hamiltonian always contains the two components. One is the operator A. Now you could think about the Hamiltonian if you want, but not to confuse with the entire Hamiltonian of the device. It's just any property. And then there is a P. operator, which is a momentum. And so momentum is the operator that is responsible for pushing the pointer, right? So arrow, okay? And the position of arrow or pointer is x. So we could always write using the, what's this equation? Ehrenfest, right? Ehrenfest equation for any observable, you could write it as the Hamiltonian of the system. Time the dynamics is defined by the essentially the commutator, right? And so if you put the interaction Hamiltonian inside, you will get well, the system part commuting with the pointer, of course, and the only part in the Hamiltonian that doesn't commute with the pointer position, right, is the momentum, right? Momentum is a conjugated operator to the position. But the commutator here will give you a constant. So the final expression will be something like time derivative of a position is proportional to the expectation value of the operator, okay, the one that we're measuring. And if we connect system with the pointer for some time, not too long, right? So then the shift of the average position will be given by the time integral, right? This coupling is switching on and off. And so eventually we get some shift of the pointer proportional to the expectation value of our system operator, right? So how this kind of pictorially can be written is exactly like initial state of the pointer is some Gaussian, let's say, function with some position, right? And then when we couple the system with pointer, then the system, because we don't know how to prepare eigenstate, we prepare superposition. So there are this well, bunch of states that have a kind of eigenvalues. And then what this coupling will do, it creates the entangled superposition now that the different states, different positions of the pointer are coupled to different positions of the or different eigenvalues or eigenstates of the system, right? So essentially we need a momentum operator to do this shift. And you could think that in the lab, what they're doing, let's say this operator that we started writing is h, and then it's multiplied by momentum that is acting on the pointer. And this is a system operator. And then we put the system in the superposition and the pointer in some position x0. And what this will result is now a different superposition, but it's going to be entangled. This is a product state. But we're gonna get, if we apply this operation, we're gonna get entangled superposition where we have all these states of the system. But now, because of this shift, they will be coupled with the different positions of the pointer state. Okay, some coefficients C. That's what we're gonna get. This entangled superposition. And when we do the measurement, we will collapse either, well, to some state of the pointer, right? So with the probabilities defined by coefficients. All right, so this is how the measurement is done. The problem with this is the operator, the one that does the shift, it's the it's a momentum, right? So momentum of the pointer. And that is, as we know from quantum mechanics, is minus I divided by h bar, multiplied by h bar, d over dx, right? So where x is a pointer position. So it's a derivative. And when we work with qubits, well, everything is discrete. Sort of, how do you organize the derivative that goes between 0 and 1? So it's not that straightforward. But it turns out what helps is to go in the Fourier space or a reciprocal space and introduce, instead of this shift operator that we can organize using momentum, right? So the usual way of shifting any function of x is just to apply the operator that is with momentum, right? So that will generate a shift. But instead, if we don't want to use the momentum, we could put resolution of identity with Fourier transformations, right? So Fourier, reciprocal Fourier times the Fourier, that's identity. And so then, if we just put that, we could see that essentially our functions will be first Fourier transformed. And then the operator that mimics or exactly represents the shift, it's going to be just in the reciprocal space, C is just a phase factor. Okay, so that is way easier to implement, as it turns out, in quantum computing. So it doesn't really require then differentiation of anything. It just multiplies by the phase that needs to be connected with the value of the function, of course, C and C. But it's just so whatever this function argument is, then we need to add an extra phase factor like this. Okay. And that's what we will do in the quantum circuit. But for that, we need a quantum Fourier transformation. Okay, so the quantum Fourier transformation is defined like this. It's like a discrete Fourier transformation in the classical physics. Let's say this is kind of the way we do Fourier transformation if we discretize our points. And in the quantum case, we just go from one linear combination to another linear combination, where x and y's amplitudes are related with the discrete Fourier transform linear combination, right? And all that, especially if you see it for the first time, is really hard to understand or kind of appreciate. Now, what will be the most important part for us, or what's the essence of what quantum Fourier transformation does? You could think of this way. If you have something that encodes the number like this state J could be, let's say, a sequence of zeros and ones, right? So, and then you can encode the number in a binary format. You can encode the number with the state J. And if you do Fourier transformation on a quantum computer, what it will do, it will produce the superposition, right, where the J will be in the phase. All right, so then you could put this number as a phase. Let's say the number is J, and it will appear in the phase. Will be K, and there will be other states. And that's sort of nice, because what we can do is that whatever number appears in the phase, we could get it back into the state by doing the inverse Fourier transformation. So that's the most useful part about Fourier transformation. It can move the numbers from the phase to the state. Right, and that's what is going to be used. Now, another nice thing about Fourier transformation is that n could be exponential. Like if we have a small n number of qubits, then the number of states in this superposition will be 2 to the n. And we only need a quadratic number of gates to do the Fourier transformation forward to backward. Right, so this is exponentially more efficient than what classical Fourier transformation can do, because the most efficient classical Fourier transformation is n log n plus Fourier transform. So that will require at least 2 to the n transformation. But we're close to the end of the hour, so let's do a small break, and we'll continue right after. Okay. Any questions online?
Arthur, you mentioned several times that how can I describe it? The product of e to the theta pk gpk equals the e to the summation of pk gpk.
Right.
Yeah, but does that require computation of the set of G, or
Yeah. So it goes through the Beck-Campbell-Hausdorff expression, right? Because if you have a product of two exponential functions, e to the, let's say, g1 and e to the g2, then you could always write it as an exponent of g1 plus g2 plus commutators of g1, g2, and other nested commutators of g1 and g2, right?
yes. So whenever G1 and G2 they don't commute, then we cannot say that the exponential of sum is equal to the product of exponential.
That's correct. But as long as we have a Lie algebra case, that simply means that there will be other linear, well, essentially there will be linear combination of G's that will represent, there will be a finite set of G's. If you take linear combination of them, they will and exponentiate that linear combination. You could represent any product of individual, I guess, two G's.
I see. So okay, I see. Now I see it. Because the theta is different.
That's
So
correct. Yes.
okay. That's where my confusion comes from. Okay, thank you.
Yeah. Theta is different, and
Yeah,
in
the
order,
theta in the product of exponential is different from the theta in the exponential of the summation.
that's correct. Yes,
Okay,
and
thank you.
yeah. That's correct, and these are actually different different parameterizations of Lie group. Depending, like you could technically write that any Lie group element is the, if you have generators G for the Lie algebra, so then you can write, I'm just using one index I, you could write them in like this or in different order, but the thetas will be different, right? So thetas will be different for different order. And you could also write it as a exponential function of the sum of thetas, and then that will be, the sum of course is order independent, but if you want to present product of exponential functions, then, well, the thetas will be, the coefficients will be different, right? As in any sequence of exponential functions. So that prime here. Does that make sense?
Yeah, makes sense. It's just maybe on the screen on my screen I cannot see the theta and theta prime difference
Okay.
in the original. I guess that's where the confusion comes from. Thank you.
All right. Yeah. Okay. Right, let's continue. Essentially, quantum phase estimation is based on the quantum Fourier transformation because we need the shift operator, right? And that's the way to represent the momentum in an easy way. And it's a quantum Fourier transformation is very efficient. Now, if you could find other algorithms where quantum Fourier transformation can be used, that could be also very valuable. Okay, and going back to this essentially scheme that the quantum phase estimation is constituted of. So it's essentially, one can think of it as a quantum Fourier transformation, red oval here. Then there is a phase shift that is going on here in the blue. And then there is an inverse Fourier transformation and measurement. So that's all it is. So now, why this is a Fourier transformation, even though they don't put QFT, which I think would be nice. I think if I were writing the scheme, like I would say that this is a QFT, then phase shift, and then QFT inverse, and then measurement, right? But they just put the Adamars, and essentially these Adamars, they do Fourier transformation, but they don't call it Fourier transformation simply because, well, the state that we are starting with is the O zeros. And it turns out that doing a Fourier transformation on that state is way simpler than doing on an arbitrary state, right? So then Fourier transformation kind of, because it's about putting, again, the state, remember what I said, the J state in the Fourier transformation is put into the phase I to pi, and then J k divided by m, right? So the J is in the phase, and if J is 0, the phase is 0. So that means all the states k now, they have the same coefficient, right? So it's k sum over k, and then divided with the normalization factor n square root of n. So, and that's what exactly Adamars are doing. They create equal superposition of all the states. This is a Fourier transformation of 0. So we are preparing to shift the state, which was in a 0. The pointer state was in a 0. So now we're shifting it according to well, our propagation. This is the shift part. And it creates this all states of ancilla after some algebra, which I will leave as an exercise. It's kind of done in the Nelson and Chuang book. Essentially, you could show that the products, if you consider that state that you obtain by doing the controlled unitaries, you're going to get the state where the, well, phi here is really in this notation, phi is the we have U state, and the H, when it acts on the U state, gives you phi U state, right? So this phi, the eigenvalue, is appearing in the phase, right? So as J before, right? So we substitute J by phi, and so now once we have a state where our answer is in the phase, we just need to get back that state, and that essentially is done by inverse Fourier transformation, because it goes from here back to the state, but instead of J, have a phi now, and we'll get some sort of maybe not exact representation, not exact value of phi, but approximation, because we have a finite number of qubits, right? So we have a approximation of the exact phase as long as like binary representation of the phase with an whatever number of qubits we have, right? So it's finite accuracy.
Does that mean if I would want to increase my overlap for quantum phase estimation by, I don't know, doing something else to the qubit before I go into the QPE formalism, then I have to do an actual QFT? Meaning if I don't initiate,
right?
You know what?
Yeah. So there is actually version. We will talk about that. I was planning to do it later because there are of course a lot of improvements on this textbook version, but one of them is actually starting with a different initial state, and that requires actual QFT, right? So these Adamars are only essentially representation of QFT when the state is very simple, right? Okay. But this is essentially what QFT is a measurement device for a complicated operator, which the assumption here, you could use this as a measuring device for any operator that you can construct what we have here is a control, right? So controlled unitary, that's what we need, the only thing. And the unitary that we need is exponential of minus I with some coefficient th. So these coefficients sort of they are selected again so that we kind of have a representation of the phase in a binary format correctly. Because when we put the phase in the binary format, we have this in the Fourier transformation, we have 2 pi I, and then whatever, if we have a phase here, now the phase is written as some number, let's say J1, J2, J3, and then dot J4, J5. So these J's are zeros and ones, right? So it's a binary representation of the phase. Now anything that is before the dot actually won't matter because it's we have it in the exponential function multiplied by 2 pi, right? So any integer 2 pi I times integer number z, right? So integer, that is just 1, right? So we lose that information and we only have information about the left that is kind of in the non-integer part, okay? So that coefficient, the t part could potentially rescale the h so that we have the important information in the part that is not integer, okay? And we can extract that. Then yeah, so any operator instead of h could be any property. This device would allow you to get that eigenvalue of that property measured in the ancilla or auxiliary qubits, right, in the binary format. Okay.
But I only measure the what's T register here?
Yes, that's right. First, yeah, T qubits.
Does it mean the second register is in the state of the wave function?
Yes,
It's
that's
stable.
right. Yes.
So I could do something with that if I want.
Yeah, if you want to, you could do some extra measurements on the unitary. Right. So far, here I kind of assumed that this unitary was the eigenstate, but it could be also superposition. Then we would get different phases that could be extracted, but the probability of extracting a particular phase corresponds to how, like, again, in your initial state, if it's a superposition of eigenstates, then these coefficients will determine the probability of getting the phase from the corresponding eigenstate. All right. Good. Now, I guess once we discuss how to do the shift, there is still a problem of how do we really make the exponential function of the Hamiltonian, because it's not well, it's not like you could say, all right, quantum computer, here's my Hamiltonian, prepare the sequence of gates that will encode the controlled unitary that has a generator, the Hamiltonian. Even if the Hamiltonian is presented, as we talked, in a qubit format, right? So it's a linear combination of Pauli products, and still there is a so-called compilation problem. How do I present the exponential function of this Hamiltonian in terms of elementary gates that quantum computer can do? Okay, in that sense, what Feynman said is like, okay, quantum, well, nature is quantum. Let's just use the quantum, I guess, objects to simulate it. It's not that simple. That's why it took 40 years before we start getting some quantum computers, and even then, still, this problem is a complicated problem. So, how do you really use the systems, quantum systems that we can control, or we can do the gates, right? So how do we really use that to simulate something that we want, right? So that's the issue here. And one of the simple approaches that probably we'll talk today mostly about is the Trotterization. So what Trotterization is you have exponential of some terms in the Hamiltonian, linear combination of Paulis, for example. And then there is a Trotter theorem that says that if you start making the parameter in front of this part small, then you can ignore the fact that they don't commute, right? So the idea here is that, as we already discussed today, if you have A, and then you have sort of, well, yes, you could go from either ways, from either side. Let's say if you have A plus B multiplied by T, then you can always present it as a exponent of A T, exponent of B T, and exponent of then the series of commutators A, B, right? I believe this is called Zassenhaus formula. Then the formula, then there is a B, say B, B3 divided by some coefficient, let's say 6, and so on. You could double check me on the coefficients, but the idea is that if the T is small enough, so then all these guys becomes they become essentially close to identity, right? But for that you need to reduce the T, and then sort of the algebra here is that you take the T reduced by n, and also in the nth power, so that allows you to essentially write this in terms of ET divided by n, BT divided by n times. So if n large enough, this is a good approximation, which is also called first order approximation, first order Trotter approximation. Now in Trotter's theorem, though, it's like k goes to infinity or n goes to infinity, right? And what one would want to do here is to pick the fragments of the Hamiltonian that are easy to diagonalize. Why? Because we can then easily exponentiate them, right? So because after doing the Trotter expansion, we still need to exponentiate the fragments that we broke the Hamiltonian into, and that's pretty much the same idea as in the case of measurement. right? Because in the measurement, we also wanted to partition Hamiltonian into groups where we can diagonalize bring them to the Z, because Z's are diagonal in the computational basis. Now we can do things in fermionic algebras, bring things to essentially occupation numbers, and go to the qubit space with that, right? So there's the same idea as in measurements, but errors in the Trotter case, of course, are different, because as you could imagine, errors in the Trotter case, they are related to the some sort of a size of the commutator rather than variances, right? So this is something, if you want to improve on the, or find which partitionings are the best for this task, then you would need to look at the sort of the error that corresponds to a Trotter. And this is exactly the question we were asking. How do we really partition efficiently? So what way is the best? Going with the qubit fragments or fermionic fragments? And in order to do analysis sort of easier, like simpler terms, we only looked at the first order Trotter. There is a higher order Trotter formulas where one can try to cancel the commutator by say taking the, as we've seen in one of this discussion about the unitaries, the commutator can be represented as a, b, and then exponential function of minus a and minus b. So there are ways to essentially present the sum as products, but products will contain not just simply a, b, but also terms. I guess the second order, the easiest way to write it would be you could write something like a t divided by, well, let's say if we already make the fragment, or like our t total time is partitioned to the delta t's. So then the second order Trotter will be b delta t. Then we have again first type of terms. Okay. So this is the second order Trotter expression. You put the n steps like that. And that could be simplified to essentially having for the first part delta t divided by 2. Then we could say that what we are doing is the normal first order Trotter for n minus 1 steps, and then the last one, yeah, I guess the last one requires this delta t divided by 2, right? So this is just a way to show that for the two fragments, at least, you could get the second order Trotter for the price of first order Trotter. But for the higher number of terms, if you have not just a plus b, but a plus b plus c, then you won't be able to do this. This is somewhat similar to when you do the numerical integration. There is a trapezoidal and rectangular scheme, because the boundaries kind of contribute from both fragments the same. Then you could actually get the trapezoidal accuracy using the rectangular scheme. Okay, so here we analyze the first order Trotter. It's just substituting the sum by the product. And then actually, interestingly, the error for the first order Trotter and higher order Trotters, the upper bound, if you want to create upper bound, that was derived only quite recently. So generally, Trotter error analysis is difficult. Things don't commute and not easy to analyze. But group of Andrew Childs co-workers, they were able to write the upper bound for the norm, and here what we mean is a spectral norm, right? So it's the largest eigenvalues possible. So now we have this norm of the difference between the two propagators, right? So one is the exact one, another is the approximate first order. And turns out that you could analyze this in simpler terms. That's what we did in the cited work there. And what I mean is that imagine if you have Hamiltonian fragments that are simple fragments, with the Childs and coworkers derived is the norms of these commutators of the simple fragments, right? And if you think that, okay, let's say we have fragments that are 2-electron Hamiltonians, then the commutator of 2-electron Hamiltonians will be 3-electron Hamiltonians, and they're not anymore exactly solvable. So finding the norm of that is actually quite complicated. So instead, one can derive the following expression where we did the upper bound of their upper bound. And the way you could derive it is simply by taking the following consideration, that the commutator between the two operators, NH and HK, it really doesn't change if you shift any of these operators, right? So you could do the shift with, say, some S and identity, and then here HK minus SK identity, right? So because identity commutes with everything, yeah.
The sun is again full unit coming up.
All right. Better?
Yeah.
Okay. All right, so this is exact by doing the shift, right? You could get the same commutator. And then what also we could do is essentially realize that now it's a shifted operators. And we could, since we are interested in making estimating the norm, right? So then the idea is that, okay, we could use any shift, but can we use the shift that, all right, so shift doesn't really change the norm of the commutators, but the commutators are not convenient things to work with. And they are essentially Hn now prime, commutator with Hk prime. So these guys, you could essentially using the condition that for any norm A times B with norms, they always going to be larger or equal than the norm of A times B. Okay, so that's the condition that is true for any matrix, or since we are working in the finite spaces, this is always true because we could represent our operators as matrices. And so therefore, we could always say that these guys are less or equal than the two norms of Hn prime multiplied by Hk prime also have a condition that A plus minus B, it's always less or equal than the norm of A plus the norm of B. Okay. So that is the second thing that we used here. Okay, so with that, now we have this expression, but this expression depends on how you shift. So you could, because this is always true, no matter what shift you put, you could try to reduce this upper bound of our upper bound, because this guy is upper bounding the true difference between the two propagators, minus I h t and product of the exponential functions, right? So the idea is that if we make things less accurate, because we went from the norm of commutators to actually norms of the terms that are in the commutator. So then at least we should use the shift that we could introduce without changing the commutator. We should use the shift to reduce the norms of the shifted terms, right? So that makes essentially if the true value of this norm, let's say norm number 1, if the true value is here, then we have the norms of commutators which are upper bound, and then norms of the products or products of norms, they, depending on how you shift, they create the kind of the entire spectrum of values, which are even higher in the values than the second case. It's here, right? So then nature of idea is to find the shift that is bringing us as close to the lowest possible value of these products, right? So is that clear? Because shifts here, they don't matter. But when we went from the commutator to the product of norms, then shifts will matter, because depending on the shift, the norm of this shifted operator will be the largest eigenvalue. And we know how to shift so that the largest eigenvalue will be the lowest. The largest eigenvalue will be the smallest among the possible. And the idea is that you see the spectrum of any operator, you could put it in one dimension. There is a largest E max, there is an E mean, and these are considering this sign, right? But if the situation is like you have a 0 here and the largest E max is here, but E mean is somewhere here, when we consider the norm, what we kind of care about is the largest absolute, right? So the largest absolute will be E mean then, not E max. Because those are just based on what's the sign of the eigenvalues. Now, since we can have this sort of freedom, what is the largest absolute value eigenvalue could be? Is it from positive or from negative? The shift, of course, changes the spectrum. All right. So when we introduce the shift, and the best shift to reduce what's the largest by absolute value eigenvalue will be is that to shift it symmetrically. Okay. And so if we do shift symmetrically, in this case, then it will be minus delta of maximum divided by maximum minus minimum. And then here there will be delta E divided by 2, right? So these are the we call again spectral range, and the optimal shift to make this upper bound the most accurate. It's the shift that shifts every fragment symmetrically. And then once you do that, it turns out that there's with a little bit of more algebra, you could decompose this expression with the optimal shift. Optimal shift essentially makes this norm to be delta E n divided by 2, and this delta E k divided by 2. So that's essentially what you get, and it's a mixed product, right? So it's a product of n times k, where n and k are different, and you summon over that. And then you could write this down simply as so if you have a sum of n not equal k, delta E n divided by 2, delta k divided by 2, divided by 2. So then you could write it as sum of En squared. So the square will contain the square generally will contain the two types of element, diagonal and off diagonal, right? So this will be delta En squares divided. So okay, with division we'll figure out later some coefficients, but it's a sum over n's, and this one will be sum over delta En delta k not equal to n, right? And we want to, because we have these guys only in our expression, we want to remove then this part, and that requires to essentially subtract sum over squares. And this could be sort of written in the form that is written there, with the kind of taken the delta sum over delta En squared. Here will be 1 minus delta En squared divided by sum over delta En squared, right? And that sum over n's here. So let's put different n's, and that is the expression that is 1 minus sum over omega n's squared, right? So this one, and so we have the sum over spectral ranges for the fragments multiplied by this part that is really entropic part, we call it. Why we call it entropic? Because this 1 minus some positive number squared, which sum to 1, it's a linearized version of the Shannon entropy, written if you have a weight like this, right? So if you do the Taylor expansion of omega goes to 0 or 1, then you're going to get something like this. And these two functions actually, they maximized at the same values of omega. That would be equal distribution again, democratic distribution between the fragments, right? So the worst case scenario for this part to be the largest is when all the omegas are equal, right? So it's it makes it like 1 over n for the omega, and that's the worst case scenario with the two factors again that we have a total spectral range. So generally we would like that thing to be smallest as possible. Smallest spread of eigenvalues is good for that. And non-uniform distribution is good for the entropic part, right? Because the equal distribution makes the entropy go up. And so this is the simple, again, illustration that greedy algorithms generally give you the most non-equal distribution, right? So if you, as a visual algorithm, if you're trying to represent the square with the circles, like if you do it in a greedy way, now the first circle will be the largest, right? And then so it will be smaller and smaller and smaller. right? So this is the intuition behind what we were doing for finding the fragments to optimize a upper bound of the upper bound. It kind of suggests that you want to use greedy algorithms that reduce the entropic part, okay? Because of course one can try to optimize the norm of commutators, but we don't know how to do it efficiently, okay? And here are some results on trotterization error. So here the exact Trotter error, like the Trotter upper bound, I guess. And for small systems where we can calculate this exactly, but we want to see how good the heuristics that we use work. So in the qubit algebra in blue, there's a greedy algorithm and non-greedy, dark blue. So as you can see in all the systems, greedy algorithms, according to our kind of prediction, work better. And then there is this red and orange, that's kind of fragments that are coming from fermionic algebras. There, the message is that, again, the same greedy orange works better than non-greedy. And in general, you could see that fermionic algebras work better than qubit algebras. Fermionic fragments are winning in all these cases. And we understand the reason for that is because in order to calculate spectral range, say, of the fragments, what, again, you could use as a symmetry, because if you have symmetries like number of electrons, spin, then your fragments, they will even fragment Hamiltonians, right? So we're talking about, let's say we have fermionic fragments, they commute with symmetries, like number of electron, spin, and the qubit fragments, they don't commute with usual electronic, like normal symmetries, like number of electrons, say, right? So in this case, the qubit case, they don't commute with symmetries. But the commutation with symmetries allow you to sort of say that the Hamiltonian, they have block diagonal structure, and these blocks correspond to different irreducible representation of the symmetry groups, right? So the blocks are not coupled. And when you find eigenvalues, they will be, well, essentially you can maximize, minimize the, well, over the blocks, right? Because, well, technically what happens is that your system has usually a symmetry. And so then only one of these blocks will be relevant, right? And so the norms that are calculated, you don't need to maximize over the blocks, but rather you could focus on a particular block that corresponds to the state that you're working with, right? So if you have these blocks, then naturally you know which block to consider, because you know let's say system has a fixed number of electrons. But if your fragments, they don't commute with symmetries, they don't have this block structure, you would need to sort of, to find the norm, maximize over the entire like the spectrum, right? And that's the reason why fermionic algebras, because they have those blocks, so they generally have lower norms for the commutators, right? And if you compare this with just a very naive approach where you take as a Pauli, like just since the entire Hamiltonian is a linear combination of Pauli products, you could do the trotterization using the Paulis instead of more sophisticated fragments. So usually that takes like that raises the Trotter error 10 times, as we've seen for this type of problems. Okay, so it's good to group again, at least based on this criterion. But that's not the end of the story. because what we realize is so far the Childs and coworkers, what they were looking at is the difference between the two unitary transformations, the norm of the difference. And what technically we're interested in the eigenvalue problem is the following, is what is the difference between the actual eigenvalue you're going to get if you take the Fourier transformation of autocorrelation function with the true Hamiltonian and the Trotter approximation, right? So it's not about how accurate the dynamics of, I guess, or what's the difference between the dynamics that is given by true propagator versus Trotter. It's exactly what's the effect of inaccuracies we have on the eigenvalues, okay? And one can ask the question, okay, how good is the correlation between the two errors, the error for the propagators versus error of the eigenvalues? And when we look at this, where x-axis is the eigenvalues errors, and the y-axis is the errors based on the norms of the commutators, there is almost no correlation, right? So it turns out that looking at this quantity as a way to predict how good is your eigenvalues that are coming out of the Trotter approximation is not a good idea, surprisingly, because one would expect the better the evolution, then the better will be the eigenvalues, right? But the correlation there is not that good. Okay. So one reason for that, or explanation, is that when we consider the norms of the commutators, there is a problem with that consideration, because these operators, they don't commute, right? So if you think about commutators of like few operators that don't commute, the commutators are also operators that don't commute. And what this means is that they don't share eigenspectrums, right? So when we sum the norms, each norm is the largest eigenvalue. So that is, we are considering some unrealistic or worst case scenario where the state that we are acting on with this, or let's say with two propagators, will be eigenstate with the highest eigenvalue for all these commutators, but there's no such state because they don't share eigenstates, right? So therefore, estimating the sum of the norms is really not even a worst case scenario, but it's a worst case scenario that cannot ever happen, right? Because this, again, states, these operators, these commutators, they don't commute, and therefore they don't share eigenstates. There will be no state that has the largest eigenvalue for all of them. Okay, so what do we do? So what we can do is we can, again, using Campbell-Baker-Hausdorff expansion, we could create effective Hamiltonian that corresponds to the essentially being a generator in a single exponential function, right? So this is on the left is a Trotter approximation. It's a product of non-commuting generators. But one can always say, all right, there is some effective Hamiltonian that we maybe don't know exactly, because it's a big or it's an infinite sum of HN nested commutators, right? But at least few first terms in effective Hamiltonian, especially if we have a parameter that we can make small, we can estimate. So this is the expression. First, we sum all the HNs, and then we have commutators and then nested commutators, right? And things become more and more complicated in this effective Hamiltonian. But we have delta t that if we make it small, then this higher, more complicated terms could be suppressed, right? And then we can make some sort of a perturbation theory consideration that after all, what the value of the eigenvalue you're going to get if you do autocorrelation function of the Trotter approximate propagator supposed to be an eigenvalue of this effective Hamiltonian, which depends on delta t. So this is the error in the energy compared to the true Hamiltonian. This one is just this part, right? So what this part will do to the spectrum of H, because, well, that's the question, right? Because we are getting the spectrum of H effective, not the spectrum of H, okay? And so this is the correction, second order correction, that tells us that the error will be proportional to these nested commutators and second order in the V1, the commutators. All right, and then if we look at what's this PT estimate, perturbation theory estimate, and the true error that we now obtain from the eigenvalues, the actual estimate is the correlation is between the two very good. We could make it, I guess, even better if we reduce the time step. Here was some time step selected judiciously. And then if we then ask the question, which fragments are better, things are not as before. Turns out that the qubit fragments actually perform actually quite nice compared to the fermionic fragments, which are not doing so great, especially for larger systems. So the lessons here is essentially perturbation estimates are way better if you are interested in the eigenvalue problem. And even though we don't have upper bounds, we have just the estimates. But it's better to use those rather than upper bounds. And so far, qubit methods are generally better. We don't have a really good explanation why. And that's something that we still trying to get some intuition about, right? Because the expressions to analyze, they are somewhat complicated. They involve these commutators between the fragments here and the nested commutators of the same fragments. So analysis is not straightforward to say which fragments will be better. Okay. And, so everything was somewhat simpler when we were considering the norms. Okay, but the norms are kind of leading us not into the right direction. Okay. All right, just to summarize the Trotter approximation, I'll probably stop here before going into more sophisticated algorithms. So Trotter error for dynamics, yeah, so it's not as good as doing the Trotter error for eigenvalues in terms of predicting the results. So we produced two papers, one about how to optimize the kind of the Trotter error for dynamics. Another is actually for eigenvalues, realizing that those two results are very different. And this analysis allows you to sort of reduce the prefactor in this case, and in this case also it's in front of the t-square, the general error of the Trotter method. If you do in the first order, it's always going to be your time step squared. The larger the time, the larger the error. And this is the kind of the situation with Trotter. Of course, you could try to reduce the time square error scaling by going to the higher order Trotter, but then it's still going to be over like higher than linear. And there are ways to go beyond Trotter. This is the new topic that I will be discussing tomorrow. It's called linear combination of unitaries. I guess I could show you preview. Oops, yeah. So we will be encoding the Hamiltonian as a linear combination of unitaries. There is a way to do it, and methods like qubitization could be introduced. So they have linear no Trotter error, and the cost of method will be scaling with the time linearly instead of quadratic. So that's why most of the work these days is focusing on this LCU qubitization techniques, not so much on Trotter, but Trotter has also some advantages if one thinks about maybe early fault tolerant regimes. The Trotter has benefits of having fewer qubits because this linear combination of unitaries, as we'll see tomorrow, it actually requires some even more ancilla qubits than the Trotter algorithm-based methods. Okay, so, but the good thing is that there's no Trotter error, which is actually quite impressive if you think about it. Because why is it sort of impressive is that if you want to put like or construct some function of the operator that is not polynomial function, then really it's not a trivial task, and yet usually you could try to do it using the Trotter type of approximations, but they will always have an error associated. And in general, of course, if the H is very simple operator, you can diagonalize, you can diagonalize it using unitaries, then you could always go into that basis and then present it like this. This is easy. But if you cannot diagonalize H, then what is the way to implement this using some sort of product of simpler unitaries? That is, well, imagine if the f of h is a unitary operator, breaking it down to simpler unitaries is a non-trivial task, general. And Trotter is definitely one way to go, but it was always going to be approximate. This LCU method that we'll be talking tomorrow, that has no error. Okay. Any questions? All right, then I'll see you tomorrow.